In a typical three-phase, four-wire electrical service, a dedicated service ground conductor, separate from the neutral conductor, is generally not required to run from the utility transformer's grounding electrode to the building's service switchboard ground bar and grounding electrode. The neutral conductor is grounded both at the utility transformer and at the service entrance of the building. This established connection serves as the primary grounding path, effectively handling fault currents and lightning strikes. However, there are specific circumstances where a separate service ground conductor might be necessary. One such instance involves high-impedance grounding systems. These systems are designed to limit ground fault currents through the use of a grounding transformer or resistor installed at the utility transformer. In these cases, a service ground conductor is essential to create a dedicated connection between the grounding transformer or resistor and the service equipment grounding conductor within the building. Another situation that might necessitate a separate service ground conductor arises with certain types of specialized equipment. Medical equipment or industrial machinery, for instance, may have specific grounding requirements mandated for safety purposes. These requirements often call for a dedicated grounding conductor to ensure reliable and safe operation. While there are scenarios where a service ground conductor is beneficial or required, it's crucial to acknowledge that its presence can also introduce potential problems into the electrical system. One significant concern is the possibility of creating ground loops. A ground loop occurs when multiple grounding points within a system are interconnected by a conductor, forming a closed loop. This loop can provide a path for current to circulate between the different grounding points, leading to a variety of issues. These issues can include electrical noise, interference, and even potential safety hazards. The circulating current in a ground loop can disrupt sensitive electronic equipment, causing malfunctions or inaccurate readings. Furthermore, the presence of unintended current paths can compromise the effectiveness of safety grounding, increasing the risk of electric shock. Another potential problem associated with service ground conductors is corrosion. Because the service ground conductor is often exposed to the outdoor environment, it is susceptible to corrosion from moisture, chemicals, and other environmental factors. Corrosion can weaken the conductor over time, increasing its electrical resistance. This increased resistance diminishes the conductor's ability to effectively carry fault currents, compromising its intended function as a grounding path. In situations where a service ground conductor is deemed necessary, proper sizing and connection are paramount. The conductor must be adequately sized to handle the maximum anticipated fault current, ensuring that it can safely conduct the current back to the source without overheating or failing. The connections at both ends of the conductor must be secure and corrosion resistant to maintain a reliable electrical path. It's important to consult the National Electrical Code, specifically Articles 250.50, 250.52, 250.66, and 250.166 for detailed requirements on grounding electrode systems and conductor sizing. In summary, a separate service ground conductor is not generally required for a standard three-phase, four-wire electrical service where the neutral is properly grounded. However, specific situations, such as high-impedance grounding systems or specialized equipment requirements, may necessitate its use. When a service ground conductor is installed, it's essential to carefully consider the potential problems it can introduce, such as ground loops and corrosion, and to take appropriate measures to mitigate these risks. This includes proper sizing, secure connections, and adherence to relevant electrical codes and standards to ensure a safe and reliable electrical system. Consulting a qualified electrical engineer is highly recommended when making decisions about grounding systems to ensure compliance with all applicable regulations and best practices. The information provided serves as a general guide and should not be considered a substitute for professional engineering advice. Proper grounding practices are crucial for electrical safety and system performance. Firstly, it's important to understand the fundamental principles of grounding. Grounding provides a low-impedance path for fault currents to return to the source, allowing protective devices like circuit breakers and fuses to quickly trip and de-energize the circuit. Secondly, the size of the grounding conductor is determined by the size of the service entrance conductors. NEC Table 250.66 provides guidance on selecting the appropriate size grounding electrode conductor based on the size of the service entrance conductors. Thirdly, the grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. These electrodes are connected to the grounding electrode conductor, which then connects to the service equipment grounding bus. Fourthly, ground rods should be at least 8 feet long and driven into the ground until at least 8 feet of the rod is in contact with the soil. The spacing between ground rods should be at least equal to the length of the rod. Fifthly, metal underground water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. The water pipe must be supplemented by an additional grounding electrode, such as a ground rod or ground plate. Sixthly, the service equipment grounding bus must be bonded to the metal enclosure of the service equipment, as well as to any non-current carrying metal parts that are likely to become energized. Seventhly, equipment grounding conductors are used to connect the grounding terminals of electrical equipment to the service equipment grounding bus. These conductors provide a low impedance path for fault currents, protecting equipment and personnel from electrical shock hazards. Eighthly, the size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. NEC Table 250.122 provides guidance on selecting the appropriate size equipment grounding conductor. Ninthly, it's important to avoid creating ground loops, which can cause circulating currents and interference. Ground loops can be minimized by using a single-point grounding system, where all grounding conductors are connected to a single grounding point. Tenthly, regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections should be checked for corrosion and tightness, and grounding electrodes should be tested to ensure that they provide a low impedance path to ground. When dealing with sensitive electronic equipment, it's often necessary to implement additional grounding measures to minimize noise and interference. These measures can include using shielded cables, installing isolation transformers, and providing dedicated grounding conductors for sensitive equipment. In high-noise environments, it may also be necessary to use surge protective devices to protect equipment from voltage transients. The use of surge protective devices can help to prevent damage to sensitive electronic equipment caused by lightning strikes or other voltage surges. Surge protective devices should be installed at the service entrance and at any point where sensitive equipment is connected to the electrical system. Proper grounding is also essential for lightning protection systems. Lightning protection systems are designed to protect buildings and equipment from damage caused by lightning strikes. These systems typically consist of air terminals, down conductors, and a grounding system. The grounding system for a lightning protection system must be designed to provide a lower impedance path for lightning currents to dissipate into the earth. It's important to note that grounding requirements can vary depending on the type of electrical system and the specific application. It's always best to consult with a qualified electrical engineer to ensure that the grounding system is designed and installed in accordance with all applicable codes and standards. Understanding the principles of grounding and following proper grounding practices are essential for electrical safety and system performance. By taking the time to design and install a proper grounding system, you can help to protect people and equipment from electrical hazards. Always remember to consult the latest edition of the National Electrical Code and other relevant standards for the most up-to-date information on grounding requirements. Proper grounding is not just a matter of compliance, it's a critical aspect of electrical safety.